This is sections 1.2 and 1.3 on points, lines, planes, segments, and rays. This section in this video is full of definitions, and the whole point is to lay out these definitions so that we can understand what we're doing the rest of the course. In all of geometry, we're basically studying figures, and the smallest and most simple figure we can study is a point. Now, a point looks like it has some size and shape, but it really doesn't. It has no size, no shape, and it has what we call dimension of 0. It has 0 dimension, 0 size, 0 shape. It's essentially the smallest we can get, which is no size at all. But if we take a whole bunch of points and we line them up all next to each other, we can create what we know is called a line. A line is a set of an infinite number of points all next to each other. Very hard to define what next to each other means. And in fact, a point and a line are both undefined in geometry. We don't give definitions to them, we just intuitively understand what they mean. Because giving them definitions would be too difficult to do. Very difficult, too difficult to do. A line has no thickness, but it extends infinitely in two directions. A line has a dimension of 1. Even though it's made up of an infinite number of things of dimension 0, an infinite number of points, it has a dimension of 1. A point we label with a capital letter. We can call that point A. A line we label with any 2 points that are on that line. So if this is a line BC, if this line contains points B and C, we can call it line BC. And line BC is written out in symbols, or denoted as BC with a bar above them and an arrow on each end of the bar. The arrows are necessary to distinguish that it's a line. It extends infinitely in both of those directions. Notice it doesn't matter which order we put them in. Line BC is the same as line CB. There's only one line that contains those 2 points. 2 points determine a line. If we take an infinite number of lines and in a sense stack them on top of each other, but not really because they don't have any thickness, we can create a plane. And the plane on our paper looks sort of like a rectangle. It's not actually a rectangle because a plane extends infinitely in all 4 directions. It's flat, it has no thickness, so a plane has no thickness. But it is infinitely large. A plane has a dimension of 2. As an example of a plane, think of a piece of paper that extends infinitely in all 4 directions and has no thickness. A piece of paper is very thin, but it has a thickness. I'm able to hold it. A plane has no thickness. It's infinitely thin. A plane is just labeled with a capital letter. We usually put it in the corner of the rectangle we draw on our paper to represent that plane, and I would just call that plane M if I labeled it as M. Again, points are a point, a line, and a plane are undefined terms. We understand what they mean, but we're not really able to give them precise definitions. Things are collinear if they are all in one line. So I can have collinear points if all of those points lie along the same line. Things that lie on the same plane are called coplanar, all in one plane. So points can be coplanar. I can have points that are coplanar if they all lie in the same plane. Lines can also be coplanar if the lines all lie in the same plane. So maybe there's a line, there's a line, and there's another line. They're coplanar because they all lie in the same plane. We know what it means for two things to intersect. The intersection of two things is all of the points that they have in common. The intersection is all points held in common. So when two lines intersect, they have one point in common. And that one point is the intersection of those two lines. We can have two planes that intersect. It's very difficult to draw on a two-dimensional piece of paper there. But think of two pieces of paper intersecting. Remember, my planes are infinite, so these pieces of paper are not the best analogy, but they're what we have. They intersect, and the shape they form when they intersect is a line. It's not just this, but it extends infinitely up and down. So since it's infinite, it's a line. So two planes intersect in a line. You can also have a plane and a line, which my pencil will represent, intersecting, and they intersect. They could intersect like that. What is their intersection? Their intersection is all the points they have in common. Well, how many points do they have in common? Just that one where the line touches the plane and crosses through. So a line and a plane can intersect in one point like that. You can also have a line be in the plane completely, so lying in the plane. Imagine the pencil is on the plane, or I could draw a line on my paper. That line and that plane intersect, and their intersection is the entire line. They share that entire line in common. We understand what it means for two things to intersect. Now I can take a line, and let's say I don't want to deal with the whole line. I'm only interested in a piece of it. Well, a piece of a line has a name. Let's take a line AB here. And if I only want that piece between A and B, that's called the segment AB. So segment, this is a definition, segment AB, which is denoted with capital letter A, capital letter B, and a bar above them. A line had a bar with two arrows on the ends. A segment has no arrows. It's just a finite piece of a line. So it just has a bar above it. Segment AB, denoted like that, consists of points A and B, and all points between A and B. Makes sense? It's the end points, A and B, and all the points in between them. That's one way to take a chunk out of a line. That's a finite chunk. Let's say I want an infinite chunk out of a line. Well, notice before we move on that segment AB is the same as segment BA. The order in which I put the endpoints doesn't matter. Let's say instead of a finite chunk of my line, I want an infinite chunk. So let's call this G and this H. Let's say I want all of the points starting with G and moving to the right, going through H and continuing on. And I'm never going to stop. I'm just going to keep taking points, keep eating them up all the way down my infinite line. That is called array. So array GH is defined like this, and it's denoted as capital letter G, capital letter H, with a bar above them and one arrow. And that arrow needs to be pointing in the direction the ray is going in terms of the points. So it starts at G and moves towards H. Notice ray GH is completely different from ray HG. Ray HG would start with H and go towards G, so that would be this ray. Okay, that's completely different from ray GH. We always, or generally, write the endpoint of the ray first, and then the other point that we're using to define it to the right of it. So G is the endpoint, so it's defined first. Ray GH, denoted capital G, capital H, with a bar and one arrow pointing towards H, consists of segment GH, we just defined what that is, and all other points P such that H is between G and P. So what we're saying is P could be anything to the right of H. I want all of those points where H is between G and P. So it's an infinite chunk of that line. If I have a line and I divide that line into two rays like this, so ray SR, which starts at R, S and moves to the left towards R through R, and ray ST, starting at S, moving towards and through point T, then I'm forming what are called opposite rays. So ray SR and ray ST are opposite rays. Opposite rays share an endpoint, and move in opposite directions. Opposite rays form a line. Now, one line that we've used in algebra class and that we're familiar with is the number line. We know how a number line works. If we name some of these points, let's name point -3, J, the point at 0, K, the point at 2, L, and the point at 4, M. And then we can talk about the length of segment MJ. So every segment has a length. The length of segment MJ, which is denoted by capital M, capital J, and no bar above it. So segment MJ has a bar above it. The length of it has no bar above it. The length of it is referring to a number. The segment having the bar is referring to the actual line segment, the object we're measuring. The number is denoted with no bar above it. So the length of MJ, denoted MJ with no bar, is the distance between point M and point J. We know on a number line we can find that distance by subtracting their coordinates. So the length of MJ is 4 minus negative 3, which is 7. I could have subtracted in the opposite order and done negative 3 minus 4, got negative 7, and take the absolute value. Distances are always positive, so it makes no sense to talk about a negative distance or a negative length. Now, when I drew my number line, I picked a point to be 0. I picked that point right there to be 0. And then I picked a point to be 1. And by doing that, I did two things. I picked kind of a starting point for my line. Even though my line is infinite, I picked a point that I was going to call 0. And by picking 1, I picked a unit length. That unit length I then repeated to find the point 2 and the point 3 and the point negative 1 and the point negative 2. Once I do that, I can turn any line into a number line. And I can take any line, because it's infinitely long, and pick any point to be 0 and any point to be 1. The bigger the distance I go to find 1, the bigger my unit length is. But that's fine. My line is infinite, so I can still mark out an infinite number of numbers on each direction, no matter where I start at 0. That's the foundation of what's called the ruler postulate. Let's take a moment and define and understand what a postulate is. A postulate, also called an axiom, A-X-I-O-M, is a statement that is accepted without proof. Proof means we are logically laying out arguments for its existence. Logically saying it is true because of this, this, and this. A postulate or an axiom, the names are interchangeable, is a statement that we're saying we're not proving. We're not logically justifying its existence. We just intuitively understand that it works, and we're going to name it. We're going to write it down so that we can then use it to prove, to justify other things down the line. So a ruler postulate is our first such postulate, a statement that we are assuming to be true, and it makes sense. It has two pieces. First, the points on a line can be paired with real numbers in such a way that any 2 points can have coordinates 0 and 1. When I drew my number line earlier, I picked a point to be 0. I could have picked any point to be 0. That's what the ruler postulate is saying. And it's saying I could pick any point to be 1. Once I do that, I define a unit length, and that then defines everything else about that line. The second part of the ruler postulate says once you've done that, the distance between any 2 points equals the absolute value of the difference of their coordinates. That makes sense. Back in algebra class, we found distances by taking the absolute value of the difference, the subtraction, of their coordinates. So we understand how that works. The ruler postulate is saying we can do that. A second postulate that we have that you're going to think is so obvious, why do we even bother writing it down? Well, we bother writing it down because we're going to use it to prove very important things later. So we need to write it down so that we are all understanding and agreeing that this is true. It's called the segment addition postulate. It says if point B is between A and C, points A and C, then AB plus BC equals AC. The length of AB plus the length of BC equals the length of AC. Now if I have that segment, I have A, I have B, I have C, and my only condition is that B is between A and C. Then AB plus BC equals AC. Very logical, right? We understand that that's true. Nothing that's mysterious or magical about that. Okay, we also know intuitively what it means for things to be congruent. Congruent means two things: same size and same shape. It has to be both same size and same shape. We can define congruent segments then as segments with, well, let's think about this. They have to have the same size and same shape. All segments have the same shape. They're a piece of a line, right? What matters is how long it is. So we could say congruent segments are segments with equal lengths. And they would have the same size. Congruent segments are segments with equal lengths. Now let's take a segment, and I'll call my segment, I don't know, DE. D and E are the endpoints of my segment. If I take a point that is exactly halfway between the two, I call it P. So I'm saying P is halfway between D and E, then P is the midpoint of segment DE. The midpoint of the segment is the point that divides the segment into two congruent segments. So my example here, DP has to be equal to PE because P is the midpoint of segment DE. That makes sense. We know what midpoints are. Here are your immediate practice problems for this video. Remember, you need to complete these problems in your notes at the end of your notes, and they will be checked for accuracy when I check your notes in class. So let's say we have this picture you'll see on your screen here, where we have plane M. M is labeled in the top right-hand corner of the plane. We have line AB that lies in that plane. We have line CD that lies in that plane, and lines AB and CD intersect at the point Q. Going up through Q, cutting through the plane, so it doesn't lie in the plane, is line EF. So EF is cutting up through the plane like this. Okay? True or false? Number one, points C, A, B, and E are all coplanar. And number two, AQ plus QB equals AB. Answer each one of those is true or false. And that is the end of the video on sections 1.2 and 1.3.